Hello guys, today I'll be talking about my new science fair project, which is called Optimization of Rocket Nozzle Design. More specifically, this project will be focusing on how to contain the plume expansion of a rocket as it gains altitude. Now, in order to first understand why this problem even occurs, we need to understand how a rocket even produces thrust. Here we can see NASA's rocket thrust equation. Now we can see that the thrust produced comes from two parts. One comes from the force that is generated from the differential pressure, which is our slipstream pressure is different from our exit pressure multiplied by the exit area, because as we know, pressure equals force over area. And the second one is from the mass flux. And mass flux is nothing but the rate of mass as it exits the rocket nozzle. And through basic dimensional analysis, we could clearly prove that this component will lead to a force, because this is mass over time times velocity over time, which is essentially F equals ma. So the first thing we clearly notice is that this VE is referring to the horizontal component of the velocity. For example, if our true velocity is going outward at this angle as depicted in the image by these blue lines, we can see that the effective horizontal velocity that will contribute to the mass flow rate force will be only the cosine of this angle. Now we can clearly see the problem. We are losing some thrust. If only we could get these blue lines to be horizontal perfectly at every altitude. Now, why does a rocket nozzle expand its plume as altitude gains? We could look at the bell nozzle. This nozzle has been used essentially since NASA started sending people into space. We can see that if there is higher air pressure than the actual exit pressure of the nozzle, it will constrict and compress this plume and make it small. Now we can see that right here there's a premature boundary separation of the flow, and this creates an oblique shock, which is not really healthy for the rocket nozzle, and can cause some problems such as explosions and other stuff that we don't want. Now we have the rocket nozzle as it is at its design altitude. At this design altitude, the rocket plume's pressure is supposed to be equal to the outside ambient pressure. This way, both of them will be pushing at each other with an equal force, therefore all the velocity is perfectly straight down. Now as you go higher and higher in altitude, the ambient pressure is far less, and this results in the high pressure inside the plume pushing outwards more than the outside can push inwards, hence it is expanded and some of the velocity is directed outwards. This way, if we take the cosine of this angle of the velocity, you can clearly see where the name cosine loss comes from. Now, there was a potential solution for this, and this was called the aerospike nozzle. You can clearly see in an aerospike nozzle, instead of there being this bell-shaped nozzle, instead there's this cone with the airflow or the pressure outflow directed around it. This way, the boundary layer basically sticks to this geometry of the cone, and hence it is able to avoid as significant of plume expansion as a bell rocket nozzle. Yet still, we can see that there is some expansion as a rocket gains in altitude. And additionally, there are some problems with this nozzle, such as the heat produced, which is why it's not used nowadays. But for the sake of the simplicity of this project, we'll only be looking at the geometry rather than other thermal properties. So let's not worry about heat. So we want to build a rocket nozzle that's better than this aerospike. Now, I thought of an idea which I call cosine loss cancellation. Essentially, you can see in this picture, here is our input, our combustion chamber. As it passes through the throat of the nozzle, some of it will go inside this small channel on the side of the nozzle's wall. Here in this picture that I I've taken from one of my CAD designs, you can clearly see that there is this channel that leads from the main flow from the combustion chamber. Now my theory is that if I can get some of this flow to come out through this small output, it will be able to expand first, and therefore it will try to cancel out the expansion of the main outflow. And hence the velocity will be almost straight down throughout like the whole main outflow. And therefore we can use this cosine cancellation in order to get a more optimized thrust. In order to test if my theory of cosine loss cancellation will work, we can first start by benchmarking some of the more common geometries like the aerospike and bell nozzle that was mentioned before by using something called CFD, or computational fluid dynamics. Essentially, we'll be applying some partial differential equations such as Navier-Stokes, and we'll be using something called K-epsilon turbulence model in order to simulate the flow around our nozzles. For this, we will be using the open foam solver. So I started by designing our typical aerospike nozzle. You can clearly see that this is a cross-section of your average aerospike. You can clearly see that the actual spike of the nozzle is this thing. Here are just the walls. These are going to be our no-slip conditions, or wall no-slip conditions. All this is going to be where the fluid can go through. You can see it goes here to this, we'll call this the throat because it's where the maximum velocity is reached, and it'll expand, and the outflow basically comes here. It creates a boundary area right here where all the air is sticking to the geometry of this nozzle, or of this spike, and it should continue down there. So let's start by observing. After creating the mesh with ANSYS Fluent, I was able to get my open foam solution files and upload them to ParaView. Okay, so now here we are. We can clearly see our geometry right here. All this currently blue region is our flow, like where the flow could go through. All this gray region is obviously our walls. And remember, whenever there are walls, we just leave like a blank, like a hole there where no fluid can pass. First, let us start by plotting our pressure. You can clearly see the shock waves generated here. Now let us go on and check our velocity. Right now we can see that there's pretty high velocity right here. And clearly, look at this angle. We can clearly see that there is expansion in the nozzle as it is going outwards. And we don't want that. Remember, we want it to be perfectly straight. Otherwise, we had to take the cosine of this angle created, and that results in our cosine loss. So let's look at our aerospike now. The normal aerospike. Again, this is our benchmarking stuff. Let us start with our pressure. There's still a shock wave, but it's you can just barely see it, and it's where it should be. We can see the shock wave is starting to form right at the tip of the spike, which is very characteristic of aerospike nozzles. So we can tell that this simulation is pretty accurate. Here I've changed the colors of the flow so it doesn't look the same color spectrum as the benchmark for our bell. Well, we can clearly see that there is some plume expansion, and this is pretty good, but I think we can do better. Here's our temperature plot. And yeah, everything looks fine right now. So now let's move on to my test setup. Okay guys, now I'll be showing you the test setup I'll be using to test my actual nozzles once I've 3D printed them. So here are all the parts that make up my nozzle. Here's the actual nozzle. And right here, let me remove this ducted tape, is where there is a ducted fan inside. Since we do not have an actual rocket fuel that we'll be using, since remember this is 3D printed plastic, so it will not be able to withstand the heat, we are just simulating the flow through the entire nozzle by using a ducted fan. Now I've also created a stand. And here it is. We can see our nozzle is standing horizontally. And now the data that I'll be collecting will be from this pitot tube that I found online. So this is a small pitot tube that is used on RC airplanes, but it is accurate enough for me to collect data that will accurately show the differential pressure around different parts of my nozzle. And I'm using an Arduino, which will receive a digital signal from this pressure sensor, which is which has an analog to digital converter, or ADC, inside. Okay. And this is extremely sensitive, so now that I just moved it slightly, it's going to be showing our velocity slightly wrong. But I think it's fine because this is just a demo and we could just offset the velocity back. And so we can start. Let's say we want to find the flow velocity to this point. So right now, this is the main outflow right here. This is our main outflow. You can see the straws all the way back at the throat, and those straws are there to break up any of the eddies and vortices that are formed by the ducted fan. Because remember, it is a propeller, so it's going to have all that turbulent flow that we don't really want in this test. So remember, this is our main outflow. Let me focus. It's our main outflow. This is our side outflow. Remember, this is the thing that we're trying to channel air from inside and through that so that it will expand first and constrict basically the main outflow. Or using cosine loss to cancel the other cosine loss. And so essentially we'll be measuring by testing the differential pressure at different points. For example, if our rocket has significant plume expansion, that means that the pressure around our main output will be pretty low, because as it expands, the pressure is much lower, right? But if we have our cosine loss cancellation working correctly, the pressure at this point should be around the same, because it's being constricted by the cosine loss from basically the outer smaller outflow. So right now I've written this Arduino code, and right now I've just written it so it measures our flow velocity. In the real test, I will be actually measuring the differential pressure, so it's pretty easy to calculate from there. So right now it's showing a negative velocity because we just slightly moved that, so it messed up the calibration. But still, we will be able to get a pretty good demo from this. Let's try to get an actual plot. Yeah, that's much better. So we can see we have our pitot tube right at our pressure outflow. So this will be measuring our outflow pressure velocity. And I made this stand so it's slidable, so we can see how there's this support material that's holding the spike in place, right? This little block the air, so we need to measure where the air is actually going to be able to flow. So we can move this down. Yeah. And here, that's perfectly positioned right where there will be airflow. Okay. And now, we can see how our fluctuations have dropped back down. So, of course, in a real test setup, I'll be changing this code slightly so that it will display the differential pressure rather than the flow velocity. But that's a very easy fix. So this is basically the gist of how my experiment works.